Welcome students. I have been discussing the salient features of nucleosynthesis beyond iron peak. And in the last class, I have discussed how the abundance curve is supporting the idea of neutron capture cross section as the responsible process for the synthesis of elements, except this very few nucleides which we call as P-nucleides. It is the neutron induced reaction which is giving rise to the synthesis of elements beyond iron. And what were the salient features of the abundance curve that I have discussed in the last class? Number one, many times people have observed large neutron fluxes from different parts of the universe, especially from the sun. So, when people have observed that, okay, so large neutron fluxes do come from the stars, it means there is a strong possibility that neutrons are emitted in the nuclear reactions at certain stages of the star evolution, and when neutrons are emitted, there is a strong possibility that they will induce the reaction. And another feature which was supporting the hypothesis of neutron induced reactions as the sole reason for the synthesis of elements was the structure of the abundance curve. The kind of steepness people were expecting in the abundance curve, assuming the charged particle induced reactions to be responsible for the formation of elements beyond the iron peak, it was not observable. It was not observed. So, if it is not the charged particle induced reaction, then it could be neutron induced reaction. And assuming the neutron induced reactions, if we see the structure of the abundance curve, it is in agreement with the theoretical predictions. Number 3, clear peaks around the neutron magic number 50, 82, 126. So, when there is a change in the abundance at the magic numbers corresponding to the neutron number, neutrons, then it clearly supports our idea that it is the neutron induced reaction which is responsible. And Coulomb barrier consideration is always there, but however, it is not the Coulomb barrier which is stopping us to think for the neutron induced reactions, because anyway things are happening up to the iron peak. But these features one has to understand, and the important discovery which have confirmed this hypothesis of neutron induced reactions is the discovery of technetium. Though there are some contradictions when you see the statement that it is not available on earth, as I have presented some data in the previous lecture, some measurements and some observations were reported by a few groups that yes, technetium does exist on earth. So, a lot of research is to be done on the occurrence of technetium on earth. So, with these salient features of abundance curve supporting the hypothesis of neutron capture reactions, now it is a time to go forward to discuss the various processes which are responsible for the synthesis of elements as part of neutron induced reactions. All right. So, as part of this, I will discuss in today's lecture S process, okay, and then R process, and then P process. So, in today's lecture, I am going to discuss the salient features of these three processes which take place after the iron peak elements nucleosynthesis. All right. So, what is the basic mechanism underlying all these S, R and P process? Remember, we are discussing about the neutron induced reactions. So, I will be focusing on S and R process, which comes under the category of neutron induced reactions. Because capture of protons on light nuclei, they tend to produce only proton rich nuclei. In the same way, capture of neutrons on light nuclei produce neutron rich nuclei. All right. But which nuclei are produced? They depend on the rate with which the neutrons are added, whether the neutrons are added to the nuclei with slow rate or high rate. So, this will decide the production of neutron rich nuclei. Fine. For example, now if you see because of the most widely occurring neutron induced reaction, that is radiative capture reaction induced by neutrons n gamma, a nucleus having atomic number Z and mass number A is transformed into Z into A plus 1. Now, the question is whether this nucleus having atomic number Z and A plus 1 is stable or not. Okay? If it is stable, then it will capture another neutron and it transforms into A plus 2. All right? That means, there is an increment in mass number by 1 at a time, and this is the mechanism for synthesis of elements beyond iron, the most stable nucleus which we see from the binding energy curve. All right. Now, what if the nucleus which is formed because of the neutron capture is unstable? If it is unstable, then it has to undergo decay. All right. Now, whether this decay will be same in all types of situations or not? It is not, because the way unstable nucleus undergoes decay and the processes after the formation of the processes which are happening after the formation of unstable nucleus, they are controlled by two important parameters which you have to understand clearly. Without this, it is not possible to understand the physics of nucleosynthesis beyond iron peak. And those two parameters which will control the way unstable nuclei are undergoing different physics processes. Those two quantities are neutron flux, the flux with which neutrons are emitted within the star, and the lifetimes of the unstable nuclei. These two will decide the decay processes. So, in today's lecture, these two parameters are going to play very important role, whether the process is S process or it is R process. So, we will discuss beautiful features of these two processes. We will write abundance evolution equation corresponding to these two processes, and experimentally what are the interesting features people have observed. So, all these things we will discuss in today's lecture. All right. So, it is the neutron flux and lifetime of the unstable nucleus which decide the processes which take place after the unstable nucleus has formed. All right. Now, if the time constant or lifetime corresponding to the neutron capture reaction is greater than lifetime of the beta decay, then we call this as S process. It follows valley of beta stability, and this S process is responsible for creation of more than half of the elements beyond the iron. So, whatever number of nucleides are there beyond the iron, out of them half of the elements, more than half of the elements are because of S process. And what is the astrophysical site of this S process? It is the AGB star. Please recollect the HR diagram that I have discussed in the initial stage. In HR diagram, if you try to understand the location of AGB star, it is a period of stellar evolution undertaken by all low to intermediate mass stars, and when compared to the solar mass, it is about 0.6 to 10 times of the solar mass, and this is the astrophysical site of the S process. All right. And assuming that 56 Fe as seed nucleus, who will initiate this S process? So, it is very clear that because of the charged particle induced reactions, elements up to iron are formed. So, naturally, after the iron peak, if you see the observed abundance curve, the abundance comes down, and we have seen that because of the structure of the abundance curve and many other salient features, it is the neutron induced reactions. So, it makes sense if we assume the starting point of this neutron induced reaction as iron 56, the most stable nucleus, okay, after the helium. So, this iron 56 as the starting point, iron 56 as the starting point, and it goes on up to the bismuth 209, bismuth 209. Why? Because beyond bismuth 209, whenever any unstable nucleus is formed, the decay is not by a specific process which we see very soon. It is not via beta minus, but the separation energy is available for alpha particle. So, because of the emission of alpha particles from the unstable nuclei beyond bismuth 209, we can consider the termination point of the S process as bismuth 209. So, in this slide I have discussed what is the starting point and termination point of the S process, and what is the astrophysical site, and what is the relation between lifetime of the neutron capture and the beta, lifetime of the beta decay. All right. Now, if the lifetime of the neutron capture reaction is less than the lifetime of the beta decay, if it is opposite, when it can happen? As I said, two important parameters we have to understand, remember, and that is neutron flux and the lifetime of the unstable nucleus. So, if the time constant of the neutron capture reaction, the time between the capture of successive neutron induced reactions, if it is less than the lifetime of the beta reaction, beta decay, or the decay constant of the N gamma reaction, if it is greater than the decay constant of beta, decay constant of beta decay. What does it mean? Lambda n gamma, lambda n gamma is greater than lambda beta. What does it mean? There will not be time available for the unstable nucleus to undergo decay. All right. Lambda n gamma is greater than lambda beta means what? See, many a times we get confused when we compare the relation between these two, which one is greater, which one is lesser, and it is very simple. As I said, it is a neutron flux. If neutron flux is more, and when the neutron flux will be more? At very high temperatures during the star's evolution, and at very high temperatures when the neutron flux is more, unstable nucleus will not get enough time to undergo decay, even though it is unstable. Of course, it depends on the half life of the nucleus, but most of the unstable nuclei, before they undergo decay, they will capture the neutron, because enough neutrons are available because of the high neutron flux, and because they are taking place at the high temperature region beyond 1 gigakelvin. All right. So, in this particular situation, if lambda of n gamma is greater than decay constant of the beta decay, then we call this process as R process. And as I said, it is continuously absorbing the neutrons. It is capturing the neutrons, capturing the neutrons, capturing the neutrons until the flux is over. So, until the neutrons are exhausted, the capture goes on continuously, and the limit to which this process takes place is neutron drip line. So, you can see proton drip line and neutron drip line in the chart of the nucleides, right. So, this is how S and R process are defined. The R process goes towards the neutron drip line, whereas S process lies close to the stability curve, because the stability of the nucleus allows for the capture of the nucleus. All right. Now, as I said, when neutron flux terminates, all neutron rich nuclei, when they absorb the neutrons, they undergo successive beta decays. Once the neutron flux terminates, what will happen? Once the nuclei reach to the neutron drip line, they have to undergo successive beta decays, and this successive beta decay will stop only when an unstable nucleus becomes stable nucleus. These nuclei which are produced, these are stable nuclei which are produced because of the successive beta decay starting from the neutron drip line, they are called as R nuclei, and this process is called as R process. All right. And because it is undergoing beta minus decay, and we can expect the chain is isobaric chain, along the isobars the decay will happen, and until a neutron rich stable isobar is reached. All right. And what is the astrophysical sites for this R process? Astrophysical sites for the R process is low mass supernova, type 2 supernova, and neutron star mergers. So, we can divide the explosive stages of the stars, which we termed as supernova, we can divide into type 1 and type 2 supernova depending on the content of the hydrogen. All right. So, I will not go into the details of this supernova, which purely comes under the astrophysics. So, the astrophysical sites regarding the R process, they are low mass supernova, type 2 supernova, and neutron star mergers. Okay. So, in this diagram, so do not worry that some numbers are not visible clearly, I will draw again in the next slide. Just try to have a look, where is the R process and where is the S process. It is close to the stability curve, and this R process is near the neutron drip line. Fine. So, this, let us take an example of I, okay. Iridium, if its mass stable isotope of I is 127, and when neutrons are available, it becomes 128 I. It is unstable. Because it is unstable, it undergoes beta minus, and when it undergoes beta minus, you will observe xenon 128, and xenon 128 being stable, it will capture a neutron to give xenon 129. Because it is stable, it will capture one neutron, gives rise to xenon 130. It is stable, so it captures neutron, it gives xenon 131. It captures neutron because it is stable, and condition between the lifetime of the neutron capture and the lifetime of the beta, that you have to understand. Okay. In this S process, decay constant of beta is higher than the decay constant of n gamma. So, it will undergo beta decay and it gives rise to cesium 133, and cesium 133 is stable. So, from now onward, whenever I say stable nucleus, it may not be exactly stable, but the long lifetime, I mean half life is so long that it is okay to consider that nucleus as a stable nucleus. Okay. So, when I say stable nucleus, literally sometimes it may not be stable, but the half life could be of 10 to the power of 6, 10 to the power of 7 years. So, we can assume that as some kind of stable nucleus, and those kind of nucleides which are not perfectly stable, they also participate in the S process, because there is enough time available for the nucleus to undergo beta minus decay. All right. So, this path which I have explained from I 127 to cesium 133 is called as S path, only S path, but here in the nucleides you are seeing R also to some nucleides. I will explain in the next slide. So, this picture gives you an idea how the formation of nucleides happens because of the S process, and this R process I will explain with some example later. So, whatever nucleides I have discussed just now, they are designated by S for sure, right. You see here for I 127 it is S, xenon 128, 129, 130, 131, 132 and cesium 133, all these are designated with S, because they are able to capture the neutrons emitted by other reactions. All right. So, this n gamma, this denotation you can see, horizontal arrow denotes n gamma reaction, because after capturing the neutron, the increment in mass number is by 1, and if it undergoes beta minus decay in case of instability, then it is left tilted arrow mark and a new nucleus can be expected. So, this is how in one chart one can expect the S process to denote. All right. Now, let me give you a beautiful example how to understand this S and R process. Before that, let me show you in this diagram regarding R process, when the nucleides undergoes successive neutron capture, they will go to neutron repline until the neutrons are finished, right. And once it is having extremely rich full in terms of neutrons, they will undergo successive beta minus along isobaric chain, and you can see this kind of arrow marks. So, this is a beta minus neutrino, right, this left tilted arrow mark. So, they will reach to a stable state, and those stable nucleides are called as R nucleus. The R nucleides and S nucleides. So, there are few nucleides which can be produced because of both processes, and there are nucleides which can be produced only because of S, and there are few nucleides which can be produced only due to R process. So, accordingly the designation of nucleus is presented in this chart of nucleides. So, let me take a part of this chart of the nucleides for better understanding of S and R process, all right. So, let us observe this diagram. I am considering say 156 gadolinium. You know the interesting feature of this gadolinium, it has extremely high neutron capture cross sections, for which it is preferred as thermal neutron scintillator nowadays, and a lot of research work is going on gadolinium based detectors, all right. And this is, I am denoting like some diagonally I am drawing a line, okay. And previously because of some reactions this GD 156 is produced. Because it is stable, it will capture one neutron and it produces 157 GD, all right. And because it is stable, it produces 158 GD. Because it is stable, it produces 159 GD. Now, this 159 GD is not stable. So, I am not drawing any diagonal line. For GD 156, 157 and 158, I am drawing diagonally lines. So, this represents a stable nucleus. If I do not draw any diagonal line, it means it is unstable, all right, it is unstable. So, what an unstable nucleus will do? It undergoes beta minus decay, right. So, left tilted one. So, this leads to the formation of 159 Tb, and now this is stable. So, it can absorb one neutron, gives rise to 160 Tb. Now, because it is unstable, okay, this is unstable. So, it will undergo beta decay. So, this gives rise to 160 dysprosium, 160 dysprosium, and this 160 dysprosium is stable one. So, it under the condition of lambda beta is less than the lambda n gamma, that is tau n gamma is greater than tau beta, as I have discussed, it is S process. So, I am now drawing the path of S process. Okay. So, this 160 dysprosium goes to 161 dysprosium, and this goes to 162 dysprosium, okay, 162 dysprosium, and this is also stable and this is also stable. So, because these nucleides are forming along S process, I am using the symbol S. Of course, not for 159 gadolinium because it is unstable, and 159 terbium as S, of course, not 160 Tb, but yes 160 dysprosium as S, and 161 dysprosium S, 162 dysprosium S, that means S nucleus. Now, because this 166 GD can be a product of successive beta decays along isobaric chains, I can denote this nucleus as R and this also as R, okay, and this GD 158 also as R, all right. And when the successive beta decays via isobaric chain happens, it can cross this 159 GD also, all right. So, because 159 GD can undergo beta decay via S path and also via R path, so this terbium 159 also can be designated using R. So, 159 terbium is formed because of the decay of GD 159 and this GD 159 is produced, listen carefully, this GD 159 is produced because of the beta minus decay of some previous nucleus, okay, some previous nucleus. So, because the terbium 159 is the product of this successive beta minus decay, we can also denote this 159 terbium as R nucleus. Now, this 160 terbium, of course, it is unstable. So, neither S or R can be used, and this dysprosium 160, I will not use the symbol R. Why? I will explain soon. But whereas dysprosium 161, I can use symbol R, and dysprosium 162, I can use the symbol R. Now, let me draw something else. After this 159 GD, I am not drawing any line between 159 gadolinium and 160 gadolinium. Remember, this is a stable nucleus. So, how this has been formed? Listen carefully. This gadolinium 160 is formed because of the beta decay as part of the R process. So, I am designating this GD 160 as R only. I am not using S here, because even though gadolinium 160 is a stable nucleus, even though it is a stable nucleus, it is not formed because of the S process, because for GD 160 to be formed as part of S process, GD 159 has to capture a neutron, but GD 159 is a unstable nucleus. So, that is why GD 160 cannot be part of S path, but it can be R path part of. Now, this GD 160 is a stable nucleus. So, it cannot undergo decay to give rise to TB 160, because TB 160 cannot be formed because of GD 160. 160 dysprosium, which is formed because of 160 terbium, cannot be designated as R nucleus. I repeat. So, the question is, why 160 dysprosium cannot be R nucleide? Because it is not product of R process path. Why? Because 160 terbium, which is giving rise to this 160 dysprosium, is not formed by 160 GD, which is stable nucleus, is not formed by 160 gadolinium, not formed by beta decay of 160 GD, because it is stable. So, because 160 GD is stable and 160 dysprosium cannot be formed, we cannot designate dysprosium 160 with R symbol. All right. Similarly, let me discuss one more nucleus, that is 161 terbium, and this is also part of R process. Now, this is unstable. TB 161 is unstable, but this unstable nucleus is not formed by neutron capture of 160 terbium. Okay? That is the reason when terbium 161 undergoes beta minus decay and 161 dysprosium is formed, okay, from this path dysprosium 161 cannot be designated as S, but from terbium 160, when it goes to 160 dysprosium, and then when it captures the neutron, we get 161 dysprosium. All right. So, dysprosium 161 can be designated with R, because it is formed by TB 161 and T by 161 can be formed because of R process. So, with this it must be clear to you how nucleides can be designated either with S or with R. All right. So, let me include two more nucleides like 158 terbium here and 159 dysprosium, fine. And just before this 159 terbium, there is one nucleus 158 sorry, this is dysprosium. So, there is 158 dysprosium. This is neither S nor R, it is P nucleus. So, please remember this. There is one nucleus before dysprosium 159, before dysprosium 159, that is 158 dysprosium. This is P nucleus, as it is not formed by S and R process. So, how it is formed? Such nucleides which are formed neither because of S nor because of R process. There are around 35 such nucleides, and Cameron in his famous paper published in 1957, he has given a name excluded nucleides. Later we named it as P nucleides. Okay. So, they are considered as a little bit neutron deficient, and this P nucleides does not contribute much to the energy production in the stars, but regarding synthesis of elements purpose, yes, P nucleus plays important role. All right. The abundance evolution of the nucleides formed in S process. So, how to write down the abundance process of S nucleides? Remember, consider few blocks kind of like a nucleus which is stable having mass number A minus 1. By capturing neutron, it gives rise to a nucleus with mass number A, and it captures a neutron which gives rise to a nucleus with mass number A plus 1. So, this mass, a nucleus with mass number A can be formed because of the neutron capture of nucleus with having mass number A minus 1, and this mass number A nucleus can undergo neutron capture giving rise to A plus 1. Now, this can be drawn in a different way also. For example, this A minus 1, it is a stable. Okay. So, let me use this symbol for the stability. So, this A minus 1 is stable, and because it is stable, it can undergo neutron capture giving rise to an unstable nucleus. So, I am not drawing any diagonal one, it can goes to a stable one with mass number A, and because it is stable, it can capture a neutron giving rise to A plus 1. There is another possibility. So, stable nucleus with mass number A minus 1 can capture neutron giving rise to say an unstable nucleus designated by A prime. It undergoes beta minus because it is unstable and giving rise to nucleus with mass number A, and by capturing neutron it can go to A plus 1, and because it is stable, if it is stable, then it can goes to another nucleus whose mass number is A plus 2. Now, this unstable A prime, because of the neutron flux, it can always capture a neutron, okay, and goes to A plus 1, mass number A plus 1, and depending on the flux availability, if it undergoes beta minus, then A plus 1 also can be formed. So, considering this process, let me write down the abundance evolution of S process. All right. So, it is dn nucleides formed as part of S process, the time dependence. So, a nucleus with mass number A is sufficient to understand the abundance evolution of S process. So, from these three blocks it is clear that we can always represent the abundance evolution only with one mass number, that is capital A. So, this can be written as number density of neutrons and number density of s nucleides and the reaction rate per particle pair when this undergoes neutron capture plus number density of neutrons, number density of s nucleides and a minus 1 reaction rate per particle pair when a minus 1 nucleus is involved. All right. So, this is how one can write the abundance evolution for the S process. Now, how to write about the R process, abundance evolution regarding the R process? See, when temperature is greater than 1 gigakelvin and number density should be very high. As I said, flux should be very large for the R process, it is number density per centimeter cube. So, dN, I am writing the abundance evolution for the R process minus N, the number density of neutrons and nuclei having Z and A, reaction rate per particle pair plus many a times not only neutron capture, there is a possibility that photo disintegration also take place. Okay? Because successive neutron capture is happening, because of which A plus 1 is there when gamma is absorbed. So, here NZA is number density of nucleus having mass number A and this is capture reaction rate per particle pair for the nucleus X having atomic number Z and this is photo disintegration constant of the nucleus having mass number A plus 1. All right. So, this is how one can express mathematically the abundance evolution of S process and R process. And finally, let me finish this class by giving a very brief information about the P process. As I said, they are called as excluded isotopes by Cameron. All right. So, it has been seen those nucleides which are not formed because of S and R process, they are lying in terms of atomic number between 28 and 60 and they are naturally occurring neutron deficient isotopes of these elements. They range from selenium to mercury and there are around 35 P nuclei and the origin of P nuclei is not still understood and many individuals theoretically and many groups experimentally, they are actively working to understand the origin of P nuclei using world class facilities. Okay? And as of now, whatever information is available, according to that, the astrophysical site of this P nuclei is type 2 supernova. Okay? And they are very rare, you can see in terms of number, and the abundance of this P nuclei, if you see, as I said, in terms of energy production and abundance, it is not very much important. Only from the point of view of synthesis of elements, synthesis of isotopes, these P nuclei are important. Slowly it is gaining momentum, the P process understanding. And the abundance, if you see, they are about 10 to 1000 times less than the nucleides corresponding to S and R process. So, to summarize in today's lecture, I have covered salient features of S process, R process mainly, a little bit about P process. So, two important parameters we have to remember while understanding the synthesis of elements beyond iron, and that is the role of neutron flux and the lifetime of the unstable nuclei. These two will decide whether a nucleus is formed via S path or it is formed along R path. So, in the next lecture, we will see experimental aspects of these neutron induced reactions in addition to some general considerations of experimental aspects of nuclear astrophysics. Thank you very much.